Welcome everyone, lecture 8.1 on discriminative graphical model. The objective today is to build on the lecture from last week where we talk about the Bayesian network as one type of probabilistic graphical model. Now we'll look at the other family of model based on Markov random fields. These have great advantages. They also allow closer compatibility from an optimization perspective with neural networks, and so they bring some natural building blocks. And we'll look at some architectures building from these conditional random field and then extensions to that. So that's the goal. Before I go in the lecture itself, I just wanted to revisit the last few slides from the last lecture because I had to wrap them up a little bit faster than I wanted. So I'd like to go back to this a few slides and also give a quick summary of the past 7 weeks so that it gives us a nice building block for the rest of the lecture. So I just want to talk about bidirectional and CycleGAN in a little bit more details and going through the slide and giving you a little bit more clarifications. As you remember, some of these generative models, by having this discriminator and generator both working together, if you could say almost competing, that gives very realistic images. I think a great example was this talking head where you have a source face, in this case a painting, and you have on top of that condition, you have some other information, maybe the facial landmarks, and using that source image, the conditional, and then the random vector, then you can generate images, in this case, generating the faces, the talking head. And so one of these type of architecture for that is the InfoGAN as an example for that. In this case, in the InfoGAN, if you remember, the main part of the generative adversarial network is those random variable Z, and that's a random variable, and so the idea is that you could use any of these Z and you should get a synthesized image from the generator. But the key aspect here is that synthesized image will be not compared directly, but the discriminator will have to make a decision if that image is real or not. Is it a real image or is it a synthesized image? The conditional GAN is bring that step further by saying, hey, when you generate, I want to also take into consideration some extra information. Maybe it's a class, like telling you generate an image of a cat, or in the case of the example that I showed earlier, is maybe landmarks. And so these landmarks will be points on the face, and this will be given to you so that the generation of the image takes into consideration those landmarks. The InfoGAN does it in such a way to be sure that the conditional these variables C don't get ignored. It makes it such a, at the end, the discriminator also needs to correctly classify if it's a cat or if it could be also a regression task if it's a landmark. So this is the typical GAN, but I want to talk about two extensions from that. The first extension is to say, I want to train, the main goal of this whole GAN is not to really train a discriminator. The discriminator is just there to help me. The real goal is to train a generator. And this whole framework allows me to train a generator. But maybe I also would like not just to be able to train generator going from my random variable to a synthesized image, but maybe I would like to go the other way around. I would like to be able to train an encoder that takes an image and encode it into a lower dimensional representation. And that's where the bidirectional comes in. And the key aspect that I maybe have glanced over last time is that you will train two things at the same time. You will train both a generator and an encoder, both at the same time. And the interesting part here is for the generator, the input will be some random vector, and then you can synthesize any image from that. And here you will take some real images and encode it. And there, what it is interesting is that the discriminator will have a double task and find out, is it like a real image with real encoding, but in the sense of encoding, a synthesized encoding of a real image, so synthesized encoding and synthesized image, or will it go with a real image and a real random vector? And so it has those double tasks at the same time. And when you do this, that allows you to train not just a generator, but also the encoder at the same time. And as I talked last week, you could also have done that maybe by having an autoencoder as the input. And we'll discuss a little bit more this next lecture, 8.2. The second part, which I also went a little bit quickly last time, and I want to discuss again, was like, there are a lot of cases where you don't have this beautiful pair data, like you have data between maybe an input and an image and an output, but there's many cases where you would like to generate condition maybe on X, you would like to generate Y, but it's great if you have the pair data, like, hey, I would like condition on this, generate this image. But there's maybe cases where I don't have the exact pairing. I have maybe a bunch of painting of a specific artist and maybe images of the real world, but I don't happen the artist and the exact image of what they were painting. So how do you handle this kind of unpaired data? So you have like X and Y, and so you have like, you would like to be able to condition on X to be able to generate Y, but you don't have the pairing. And the idea here is really cool of CycleGAN. It's really interesting. Is the idea is that, okay, I want to learn this generator G. That's what I want to learn. I want to learn how, based on X, I want to be able to generate Y. But I don't have, like, to be sure that the Y was done the right way, I don't have that exact pair thing. So what will I do? I will say, hey, what if I had, in fact, two generators? I'm going to learn one that goes from X to Y, but I also want that learn from Y to F. And then my loss could be just like, how well did I regenerate? It's almost, you could say, almost autoencoder, like you encode and you decode. You could imagine a bit, but it's not just any kind of intermediate representation I'm going to learn here. Here, I want to learn one that, in fact, look like something. So for that, I will, in fact, having two losses. And that's the interesting thing, is I will take some image from X, I will generate Y, but in such a way that the Y is able to regenerate. That's kind of the autoencoder. But I will also do it the other way around, where I will take some image from Y, generate an X, and generate back the Y. And by doing that, and by tying the weights so that the G's are the same in both cases and the F are the same, like the same generators and the same weights, then what's really nice, I have two losses, like trying to make them, whatever I created, I synthesize as close to as close as the original. By tying these two together, and by tying these two, I will, in fact, being able to train jointly like both generators. So I will be able to go from X to Y, and I will have got for free also the Y to X if I need that as well. And that was really impressive work that came from that, the results from a photograph. And then because it knows like the style of a specific painter, it was able to switch to this, how Van Gogh, Cézanne, or some other painters will be doing that. And they will, if you have your X and Y, maybe both are images, but some are taken during the summer, some are taken during the winter. Even though you don't have the exact same landscape in winter and the summer, you can swap them around. So that was really interesting. So this is CycleGAN. There's a lot of great things with these architecture, a little bit on the challenge on the optimization, and we'll discuss a little bit more that next lecture. But I want to talk today about probabilistic graphical model to continue the lecture on Bayesian network. And to be able, one thing I wanted to do is like to be able to put that into the context of the whole course. Like we're in week number 8. Where are we in this? Because we had those 5 challenges, and we look at representation. We look at representation, joint representation, and coordinated representations. We were not done with representation. We also look, GAN is also a way to learn representation, and we'll talk next lecture about variational autoencoder. This is a core aspect. If you can represent your data, your multimodal data efficiently, that take into consideration the complementarity between modalities, this will help. This will help. A second challenge was alignment. I have aligned elements from different modalities I want to align. We look at all of the attention-based models, the self-attentions, and also look at techniques that look specifically for time series, like dynamic time warping as an example. And we looked last week at extension of that also with the soft dynamic time warping, and we'll look at a few others examples. And then we look at translation models, and one example that I particularly like was the module network. So as an example of translation. And as we know, for translation, to be successful in translation, you need to be able to do good representation and good alignment. So translation is really building on top of that. The lecture today and the lecture, the last 7.2 lectures, was really about fusion. And it's about a step further than representation alignment, and it's about fusion. And it's about doing the prediction, and it's multimodal prediction. And so when we talk about fusion, it can be sometimes a little bit ambiguous and maybe sometimes confusing to compare fusion and representation learning. And I want to both acknowledge and help a little bit in somewhat getting a little bit more detail about the taxonomy that we're using in this class. The fusion is, if you have to look at it from like input and output, representation learning is the idea that I have some input data and I want to learn a way to better represent, and better is on purpose I'm using it in generic sense. It could be better because it is smaller, like more compact. It could be because it summarizes the information. It could be because it emphasizes some aspects like semantic out of it. So this is representation learning. But at the end of the day, in many tasks, you have a prediction to make. A prediction because it's maybe a classification task, it's maybe regression, or could go all the way to generation, but we often will go there with more as a translation task, a translation where you're generating. But in many cases, you're predicting. But what you're predicting, like let's say you're predicting emotions, but you're also predicting maybe, let's say, the personality, or you're predicting like, is it a noun or is it a verb or some aspect of syntax? These predictions also can have some these labels could have some structure in it, and that's where these graphical model, and that's where fusion comes in. It's like when it's time to make that prediction, when does fusion and representation, fusion is closer to the end point, like it's like closer to the final prediction. And it's true that in neural network, for many neural network, it gets ambiguous where the representation ends and where does the final prediction happen. Is the final prediction only the last layer and everything else is about representation learning? It's almost a little bit philosophical. So I will not in this class try to argue where does fusion and representation learning ends and start for neural network. But for some other model, like probabilistic graphical models, there it's a lot more obvious that these are a lot better, or probably better suited for fusion. Because one of the great advantages of probabilistic graphical models is that you can integrate them a lot of domain knowledge. You can bring domain knowledge that we got from talking to experts or from initial analysis of the problem, or you can also just create a research hypothesis and then test it by testing different graphical models. And so domain knowledge can be done because you have knowledge about the latent substructure. By latent substructure, I mean the labels may be like emotion, like this is what you're trying to predict, but you have knowledge that this label, to be predicting it well, there is some hypothesis, there's some models, experts have studied this process. And as we've seen as an example last week, emotion, if you take the appraisal theory, could be seen, can be formalized with a structure that looks at balance, how you perform and how much effort you put, gives you some aspect of balance. And that will also focus, how much you focus on the, as a person, will all come together to finally infer the emotion. And your graphical model allows you to put that domain knowledge. Now, how do I infer learning, performance, and focus? This is where representation learning will come in. And that's why when I'm thinking of graphical models and neural network working together, I think a lot of the graphical models makes more sense on the later part, like closer to the label, because that's where you would like to put the domain knowledge. And for the more high dimensional input data, then let's be data driven and let's just use really good infrastructure that we got in neural architecture to get a better representation. And so graphical model allows you to learn if you have knowledge with what is underneath your emotion, something that's latent. Or there's also domain knowledge between your labels. And so maybe there is knowledge that like certain labels, there's a structure between my label. There's like example here is the temporal structure, meaning my emotion at time t is very likely to be dependent of t minus 1. This is an example where there is temporal information. And so at that point, graphical model can help. Example of structure prediction. What's called image, some researchers call semantic segmentation. I could predict every pixel by itself, but predicting is this pixel sky, and doing each of them independently does not make sense. It makes a lot more sense to take into consideration my neighbors. My neighbors, neighboring pixel will, when I predict my label for this pixel or for this pixel, I want to be able to predict it like all together, and I should take into consideration all of those predictions should be coherent together. And so another word we could almost say is like that structure we want to enforce some kind of coherence in my labels. And that's an example in language. It could be from dependency. So if I'm predicting what is maybe the part of speech tags from this or from this word, there may be a dependency between like coherence or dependency in coherence in like predicting them. And so I want to predict in them maybe and take into consideration that structure between the word, that link, that coherence. And that's what the graphical models do so well, or at least allows us to do. And so these are two examples. And so last lecture, we talked about Bayesian networks as a way to be able to model this, like take that domain knowledge and model it. And they're great. And I still love the Bayesian network very much, but they come with a challenge. And when it comes time to take Bayesian networks and on top, bring them with neural networks, optimizing them gets a little bit challenging. And it's part of the reason we don't see as many of them probably working together. Although there is some great work pushing the envelope in that direction, but the optimization is always one of the sticking point there. The Markov models nicely and their formulation brings a formulation that streamlines a little bit more the optimization, and bringing neural network with Markov model is a little bit more streamlined. And so so I'd like to discuss them this lecture and gives you examples that bring neural networks and Markov models. And to kind of introduce Markov models, I will do a small historical detour, also because one of the first multimodal paper using neural network was in fact using some very similar model to Markov model, and it's a restricted Boltzmann machine. And I said I will revisit it, so I promised that, so I will. So let me revisit the restricted Boltzmann machine as an introduction for the Markov models and the conditional random field specifically as a Markov. But if you remember, and I have 2 or 3 slides just to remind you, the Boltzmann machine was in fact one of the first paper, very close in time with the multimodal autoencoder papers. And there, one of the key aspects of it is that this is a generative model. An autoencoder go from text, go to the intermediate representation all the way. Autoencoder will be go to the text and come back, or the multimodal autoencoder was going to the intermediate and recreating the text or recreating the image. The generative model, what it means, and now you know it because of the last lecture, generative model means that I'm modeling the joint distribution. And so I'm modeling the joint distribution between, in this case, between text and images. And it will be trained also by looking at the joint objective with text and then hidden representation. And so you will, from a training perspective, we do it layered wise. That's what we hinted at earlier on. Before going into the math of this model, I just want to remind you that one of the advantages of the Boltzmann machine is once you learn it from a generative model perspective, then if I have a joint representation, I can decide to go either way. I can go back to text, or I can go back to images. I can go any way I want, every link. And sometimes you will see it with 2 arrows, or sometimes you will see it with just 1 line with no arrowhead. This is just 2 different ways to present it. And so the multimodal deep Boltzmann machine allowed you to go from image to text, or from text to image. It allowed you to go both ways. And one of the coolest results from this paper was that if you have a task like finding image retrieval, which is primarily often based on the data from the image, but what was really cool here is that the text, by adding the text during training of paired data, adding the text and not just taking the image representation, but using, in fact, the text as part of the how do you embed each image. So how do I embed my image? Instead of just embedding my image with VGGNet, I'm going to embed my image with the Boltzmann machine, which was trained with the text. So it was trained to kind of being a little bit closer to text. And so by doing that, it does improve for image retrieval. But the question is, what are Boltzmann machine, and specifically what's the restricted version? So restricted Boltzmann machine is an undirected graphical model. It is a graphical model. It's a generative rather than discriminative, as I already mentioned. The connections are only defined between the visible and hidden unit. It is not defined between each unit in itself. Like, so within a layer, I don't have connection. There's no structure between them. I don't enforce that. And that's what makes it a restricted Boltzmann machine. I'm about to introduce to you a Boltzmann machine in itself, but the restricted Boltzmann machine is the one that does not have any link between the random variables from the same layer. And the reason people will do restricted Boltzmann machine is that it simplifies inference. That's one of the reasons. Mathematically, the restricted Boltzmann machine, it is an energy model. And I don't know how many of you heard that term before, but if you work with conditional random field, which we're about to talk about in a little bit, these are often sometimes called also energy models. And I'm going to define to you why the term energy models, because some of you may not realize why energy model, why conditional random field is an energy model. It's because it's coming from a lot of these different models like the Boltzmann machine. But the idea of the Boltzmann machine, so you want to model the joint probability. That's what you want to model. That's a generative model. And theta here are your parameters. The parameters are the weight. Let's say you have one weight for each of these link here. And bottom term is going to be just a normalization term. And this is just to say, because it's a probability. But the most important term is the top term. And this one is defining how a specific instance, okay? So X, let's say that X is 0, 0, 1, 1, 1, 0, and H is 1, 1, 0, 0, 0, 1. And let's say that that's my X and that's my H. What I want to know is what the probability of that event to happen. What's the probability that, and because it's joint probability, what's the probability of both having X being 1, 0, 0, 1? I forgot what did I say. And then the other one being 1, 0, 1, 1, 1, 0. What is the probability of both of them occurring? That's what this is really telling me. What is the probability that both of these events happen, these multivariate events happen? And the way to do it is I'm going to compute the potential of these events to happen. And then I will divide by the potential of all possible events. And as you can imagine, because it's discrete, I can do the summation. If these events were represented more like a continuous variable, then I will be needed to integrate. But this equation, what it shows you, it says like this is the potential that the event that I currently have quantified by specific states. How is it that it's likely to happen? What's the probability of it to happen? I just divide by all the events. And an event to happen, how do I know if the event is likely to happen? For that, I will look at all of these links. If you remember, I don't link the the variables within a layer. So there's no link there, but the most important part are the link here between X and H. And so all of these W these weights are really going to define how likely. So if the weight is really high between X1 and H1, very high weight, and suddenly, let's say this one is 0 and this one is 1, this is not something I want to see. This is not compatible. This is not a high potential to see this. And so, but if the weight is really low, then I don't mind that these are different, maybe. And so that's what this is going to do. And then there will be a bias terms. But the main one is what's called the interaction term, where we're defining how each of them, and this will be just like a bias, like is X more likely to be 0 or more likely to be 1 kind of bias you could imagine. And so, but the main one is like compatibility between that. And so this is the restricted. But the normal Boltzmann machine doesn't have these restrictions and allows to have any of these to also be linked. And now this, if everything is linked with everything, this is equivalent to this representation. These two are exactly the same. And that's where, like, historically, the Boltzmann machine came first, and then the restricted came after. The Boltzmann machine was like, hey, I have the world, and I observe certain states, X, but certain states, I don't observe them, but I know they exist, but I don't observe them. And I want to know how likely, and then how likely P of X, or maybe if it was one of the thing I want to do, I could go P of X given H, or P of H given X, or I could just go P of X and H. But the idea is that some of them will be observed, and some of them will not be observed. And that's the Boltzmann machine. The Boltzmann machine, and why we call it energy model, is that it comes from statistical mechanics. And you could see it as almost atoms. It was not exactly developed for atom, but like it's like if this is a very high energy, like thermodynamic, like, and is it possible to have all of these activated at the same time? And maybe not. If they're all activated at the same time, maybe an explosion will happen or something. So the idea of the Boltzmann machine was that, like, hey, I have like I'm gonna define between each of my random variables some kind of interaction term, some kind of potential function that, like, how much potential is it that these two co-occur at the same time. And I will use that, and the idea is like, give me any kind of states, and I will tell you how likely it is that these states exist in the real world. And the core aspect of it was this energy function. And the energy function was like, hey, I have these different states, and how likely is it that these happen? And then it was divided by the Boltzmann constant and the thermodynamic temperature. Now these days, these have been removed. We don't see that in typical conditional random field and all this. But the core of it stayed. This equation is very similar to the previous one. Of X and H, is just that they're just put together instead of having separate observed and non-observed. Originally, everything was observed, or maybe everything is non-observed, but it was, but in their case, maybe everything is observed. And so this is the idea. The same idea is that I have some state, I have the potential of this happening, and then I divide by all of the possible other events, and then that gives me a probability. So this is also called Gibbs measure, Boltzmann distribution or Gibbs measure. That's what this is. This is a very key equation for a lot of models. And we will use that because the Markov random field is just building from that with a slightly different naming convention and allows a little bit more flexibility. But the Markov random field is a lot like a Boltzmann machine. The equation is there. We drop the constant. The constant from the Boltzmann machine is not there. But the core idea is the same, is that I have random variable, and my random variables are going to be non-observed, usually a random variable or non-observed, at least not directly. And for each, for this whole link, for all these random variables, I will have this potential function. And this potential function, will be defined by a series of, you could say this motor potential function will be defined with a series of smaller potential function. And these are all these links, these different links here that I have. Each of them will be defining a potential function. And we'll go into more details in one. But for now, you'll say for each of these links here, I will have one of these potential functions. And it could be just simple. It could be, hey, is it likely that these two events happen together at the same time? And it could be a simple yes or no, like yes, they are very likely when they happen, and I give a very high potential, very high score if they co-occur. Or maybe not. When they co-occur at the same time, this is the opposite. I want them to be in opposite end, and that would be another kind of potential. The algorithm will try to take all of these potential and try to find and maximize, or try to optimize it such a way that you get all of these mini constraints taken care of all at the same time. And so this formulation is often, we call this potential function, and we call this energy function. So you will see both of these terms. So potential is the exponential minus the energy function. And the reason of this naming convention really comes from the Boltzmann machine originally. And so this is fully connected. It's very rare that you will see a fully connected Markov random field, although they will see some, and I will show example, and you will usually need to do some approximations to be able to optimize it efficiently. But in many cases, the random field, that graph, that graphical model will in fact have only a subset of the potentials defined. You could call them linked, but the potential. So instead of having all of them connected with each other, you will use some knowledge. I mean, if you have no knowledge, let's connect everything and just wait and hope that I have enough data and I can optimize things. But if I have knowledge, then I can say, hey, there is in fact some information. I know that these latent, or I hypothesize that these latent states will be connected together. In that case, as I mentioned, I will only define my potential over these links. Instead of connecting everything with everything, I will only connect it. And then, so the potential in this case will be like, I have a potential between 1 and 2, and it has its own weight, own parameters. I will define a potential function between 1 and 6, and each of these pairs. This is called Markov random field, and this is the representation that you will have for these potential function. I want to introduce one thing here that's really interesting. Is like, this is, I'm representing here is like every possible link is pairwise. But what if I wanted, in fact, the potential to be defined between 3 different variables, like maybe H5, H6, and H2? I need to know those 3 random variables to be able to know if this combination is likely, has a high potential of happening. And the typical Markov random field graphical representation, graphical model representation, does not offer that. So using graphical models to represent Markov random field gives some constraint on it, because only you get only these pairwise relationships explicitly represented in a graphical model. And this is why people, and one of my preferred representation is in fact factor graphs. It's another ways to represent the Markov random field. There's the graphical model way and the factor graph. And the factor graph here, if it's only pairwise, it's only, in this case, gonna just add this new factor, which is a square. But the power of it is that you can also start putting factors with maybe some observed variable, because all of this is all my latent variable. But you may also have observed. But the more interesting is this one. Here, I can suddenly connect 3 things together and say, hey, high potential if H5 is 0, H4 is 1, and H3 is 1. Let's say, and or some other combination. Now I have these trinary, if you would like, I'm just creating words, to define over my latent variable. So in the same network, I will have pairwise, I will have triplets, and it can be as complex if you want, although this function will become more complex. And I could also have unary, and the unary will make a lot more sense in a second when I start introducing also observed variables. But let me come back to this one. So this is factor graph. And this is called also what's called a clique factorization. I know it's a lot of terms. I apologize for that. But now when you look at this, there's a clique. And the cliques are, what are the variables together? What is the smallest that I can to compute my potential? And for all of these, it's all pairwise. So that big, the idea of clique is a little bit like when I look at my graphical model and I factorize it. And the clique is this way of factorizing. And so I'm going to factorize by having all of my pairwise potentials. And I will factorize also maybe the unary, and more importantly, like when I have my triplets. So now for this factor here, I can't just use H4 and H3. I need H5, so I need all 3 of them. So my clique to be able to infer that potential is going to be at least these 3 nodes. And so if H3 was also connected with, if that potential was also connected with H2, then my clique will be these 4 together. The reason I go and talk about factor graph is that now I can visit the classic problem, sequence prediction. I have a sequence of observations. I have many observations, and then I want to infer something about these latent states. And this is a little bit similar to an HMM, okay? So this is like at every point in time, I have potential. And so I define a potential. I define potential between my latent variables. And a latent variable, if you remember, is maybe it's a binary. It's like 0 or 1. or it could be a discrete, like maybe 0, 1, 2, 3, 4, 5. So this is the H1. The same for H2 can be maybe from 0 to 5, 0 to 5. And then I have potential between them. I could decide to tie the weight. I could say the weights here are also tied to the weights here are also tied. So these weights could be tied or untied. And then I could say, but this latent variable is not just has like a dependence, it has a link. And I use the word dependency. And I know in the HMM, we're going to talk about probabilistic graphical models. When we talk about the Bayesian network, like this link here will be through a conditional probability that you define these. In the case of the Markov random field, the main difference is there's no restriction to have these to be probabilities, as long as they're like any value from like minus infinity to plus infinity, although you probably want to keep it in a smaller range for just numerical stability. But there's no constraint that these are probability. And that's why they're like, you should not see it as like H of H2 given H1, which is the way you would look at it from a HMM. No, here this is just like, this is a symmetric relationship, like how likely these two events co-occur at the same time. That's the simplest way to see what is the potential that these two events co-occur at the same time. That's the way to look at this. And the formulation looked like an HMM. I could have put my X here explicitly, and that's what it is. But the big difference is I don't define it as a conditional probability, the dependence. I will look at it as a symmetric. How are those two events to be co-occurring at the same time? How is that event, latent event, to occur at the same time as an observed event? That's the way to think of those unary potential. How I have some observed event and maybe me smiling, and I want to have my H that is going to model all the different emotion maybe. And if you remember, like in the HMM, this latent variable is like 0, 1, 2, 3, 4, 5. It doesn't have a direct link to the label directly. Maybe this will be in fact predicting a sequence of happy. So the label will be more like you're going to have one model, maybe a Markov random field for happy, and then you have a Markov random field for sad, and then what so you'll have a set of parameters for the Markov random field for happy, and then a Markov random field for sad. And then I give you a video sequence, a bunch of video sequence, and then I see which one match better. I give you this and this input, and then which one match the better. And so I can look and find what is the probability, which one has the largest probability or likelihood in this case, not just probability, but likelihood. And that will be my way of using something like an HMM or Markov random field for this. And so I know it's a little bit abstract, so I would like to revisit our example, but look at it from a Markov random field perspective. Like, how do I use this from a Markov random field? How do I do it? And I will start doing it with a graphical model representation where only things can be pairwise connected. And so in that case, I will follow the same kind of thing as I will have for a Bayesian network. But the difference here, you have to look, because it's not directional, it's both ways. What it means is it's not like P of H P of X given H, or it will be modeled with this kind of link here. But no, what I will model here is like, what is the potential of both, let's say learning is a binary, like learning is either high or low, high learning or low learning, what is the potential of a high learning and a high number of book that I viewed? And let's say number of book can also be binary, like high number of book that I viewed or low number of book I viewed, high number of nodes or low number of your nodes, high number of posters, low number of posters. So the potential is because it's a symmetric relation, is really looking at how these co-occur, how are these co-occurring for performance of high number of correct answer and high performance, or low correct number of answer and low performance. And similarly for the valence, I will start looking at a high learning, what's the probability, not probability, but potential of having an event of high learning and high valence or positive valence, and low learning and high positive valence. And then I can do positive valence and high performance, positive valence and low performance. This is example of what will be modeled by each of these links. This is the graphical model, and then you can add to this all the different links that I previously had in the other. But the factor graph gives me more flexibility, and I like this a little bit better. And like, so if you look at all of this, like, where will it make sense to not just have a pairwise, but have like a meta node that will really take into consideration not just pairwise, like learning with valence, performance with valence, and then personality with valence, each of them separately. That's not really how the model was originally designed. Like, if you remember, like when we look at the theory of emotions, the theory of emotion, it was saying that it is jointly that, like, maybe I have praise and my personality together. And so, like, instead of having these separately, which would be the simple way of putting factor graph, is like keep exactly the same link and make it as a factor graph representation. And if you look at this model, like how many of them are pairwise potential and unary potential? How many unary and pairwise? Pairwise are between two random variables. So you have 1, 2, 3, and 4 pairwise potential, and unary are between random variable latent and then with observed variable, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11. So, but how to improve the factor graph? As I mentioned, this is a nice way. What I like of this representation, now it makes a lot more sense to me, because the decision of valence is not just pairwise. It's maybe a contrast between learning and performance. It's like high learning, high performance, or high learning and low performance. That's the contrast between these two that is really useful. And if I just do pairwise, this will not be explicitly modeled. But now I have a way of defining a potential function that could model that contrast really more easily. And I could have contrast also between my valence and my personality to focus. That is another way I could better represent that. So if you ask me, this is a better way of representing that model, taking into consideration. So this is an example of building a factor graph and Markov random field. But these models come, these are generative model, in fact. Markov random field, the basic Markov random field, in fact, is designed to optimize P of y given x, P of y, the emotion, no, not P of y given x, I said generative. So P of x and comma x, P of y, comma x. So P of emotion and these events. So that's a generative model. but I would like maybe, and may want to not model the joint distribution, but I may also want to model the conditional random, the discriminative. Maybe I would like to have a discriminative random field. And that's what the conditional random field does. It says, okay, now I'm not going to model P of A, Y, and X. I'm going to model P of Y given X. And so that's the main difference of the conditional random field. The rest of the formulation is a lot like a normal Markov random field. I will define that probability P of Y given X using potential function, which are defined with both pairwise potential and unary potentials. And so that tells me, and maybe I have one X for the whole sequence, or it could be many X, one X for each of the time sample. And then finally, one thing that I will do in a typical conditional random field is I will often tie the weights. So the weights for these will often be tied with this, like the same way. And that will allow me, if I don't do that and I don't tie the weight, then I will need to have a set length for my conditional random field. If I tie the weights, then it allows me to nicely have it so that I can have any sequence length, because then these potential function is exactly the same as this. The parameters are the same on both. So this is what the conditional random field, the typical one, is like. It says where you have one potential function, maybe for defining the relationship between X and Y, and then you will have a unary, and you will have tied the weights between each of the pairwise and each of the unary. And when the conditional random field was introduced, instead of calling them potential function, or calling them energy function, they decouple it, and they just call it feature function, but it's just another name convention, unfortunately, that got so now potential function, energy function, feature function, they're almost the same up to some exponential of each other. So just unfortunately there's the naming convention. And how do you optimize? What's really nice with this is that this has a nice gradient that can be computed analytically. You can compute this. I did it myself during my own PhD. And you can compute it specifically. You can optimize inference. You can gradient if there is no loop. If it's loopy, then that's going to get a little bit more challenging. But if it's a chain, or if it's a tree, then the inference can be done. And often the inference can be done with belief propagation, or like a forward-backward kind of algorithm. And so one of the first application of this was in fact in text. And I will, if you ask me, these are wonderful for text. And these were, in fact, that's a 2003 paper, I think. If you remember back in the days, the text was also represented as a one-hot encoding. So it's a 10,000 length. That's what this often were done. Now these days you will do word embedding and all this. But why is it so cool that the when you have a one-hot encoding is that X is going to be a bunch of 0 and 1. And maybe your label is like also 0 and 1. Like, is it like happy, sad, or is it a determinant, or is it the beginning of a noun phrase? Like, so if you have Y bunch multivariate, but bunch of 0 and 1, and the same for the X. What's really nice with this is then the potential function are really intuitive, because they're just like, hey, are these two events, these two events, just high potential of co-occurring at the same time, is that word very high potential of co-occurring with that label? That's what this model is going to tell you. Now, if you start using like a word embedding where it's no more just 0 and 1, but a continuous value, then the potential function will have two tasks at that point. One is to know, is these two events likely to happen, but also it will need to kind of normalize your feature to be in the same kind of range as the others. You could do it yourself and help the model, but if you don't, then this is going to have the parameter associated with it will have to normalize it for you. And that's why when you have binary output, very 0 and 1, and the output of a neuron, if you make them very sharp, like they're almost 0 or 1, like if depending which activation function you have. So it makes sense that you could use the output of a neural network, depending on what you may want to tweak, which kind of activation function you use right before the CRF, just to make it a little bit easier for the CRF. So for the task of binary, the shallow parsing, it is like detecting the non-phrases, like beginning of a non-phrase or continuation of a non-phrase. So I ask you if there's three labels, like beginning of a non-phrase, continuation of a non-phrase, or others. There's three labels. How many parameters here between? Then let's say my vocabulary is 10,000. I have 10,000 and I have three labels. How many parameters here do I have? Okay, it will be 3 times 10,000, so 30,000. And what does it learn is how likely that word co-occur or happen, potential that this co-occur with the beginning. That's what this is going to learn. And what the E is going to learn is going to be a transition. What is it? How likely that what's the potential that if I have a beginning that I will have no continuation, and one thing is like if I have a beginning, how likely that I have a continuation. And so this is what you will get from these potentials. But in many cases, you don't want to just model directly observed to the label. You would like to have something in the middle. You'd like to have some latent process. And the latent dynamic CRF is a nice little extension of that. And in this case, is like if you would like to do something like do prediction of non-phrases, it will be a very easy task if someone had manually annotated the part of speech tag. Because once you get the part of speech tags of the word, it is almost a straightforward task to do. But there's this like latent, and you don't want to manually annotate it, so you're going to just put it as a latent variable. Like, and you're going to maybe the number of state here may be similar to the number of known part of speech tag for that language. And so, and what you will do is you will say, you will have some hidden state associated for the beginning of a non-phrase. You will have some hidden state associated with the others, and then some of them for continuation. And then we can nicely, if you do this assumption, which is an interesting assumption, is you say, for each of my label, I will have a subset of hidden state. If you do that, then the latent dynamic CRF end up being mostly the same equation as the CRF, but with a different kind of summation. And that summation just correctly assign hidden state to their label. That's what it does in the CRF. And so with the LDCRF, how many parameters here? If I have 10,000 and I have 12 of them, so it will be 12 times 10,000. And what does it learn? Here is a kind of a clustering. It's a clustering that happened. It's a little bit like the HMM. Latent variable are often, you should see them as clustering. What it does, it takes those 10,000 words and cluster them in 12 different bins. 4 of these bins, if you cluster anything in 4 of these bins, it's going to be supposed that it is related to the beginning of a noun phrase. If you cluster any of those 10,000 words in the middle ones, then we'll suppose it's a continuation. And if you cluster a word in the last 4, then we'll suppose that it is the other one. And so that's what you will learn here. It's kind of a clustering with the theta x. The theta e is interesting because it's going to learn 2 different things. It's going to learn what's called intra-class dynamic and between class or cross-class dynamic. It will learn within a class, like within like all of these beginning of a noun phrase. Like, what is the probability to go from B1 to B2? What's the, not probability, but what's the potential to have both B1 and B2 co-occurring at the same time with these values? What's those co-occurrence or potential of B2 and B3 to co-occur? That's the intrinsic dynamic. The more interesting is extrinsic, what it is from B1 and co-occurring with I1 like at the next time step. That's extrinsic dynamic, and that's really interesting because now your model, your hidden dynamics here is going to model both within the label and between labels as well. And when you do it in real data and you learn a model with this, and then you look at these predicted hidden states, it's really interesting because you see that effectively the text ended up being clustering. You never told that B1 should be about specific part of speech tag, but what's really interesting is that it naturally cluster it for you. So B1 ended up being a lot more determinant pronouns, and that's the beginning of a noun phrase. The house or the greenhouse, very likely to have a determinant of a pronoun at the beginning of a noun phrase. So it not only learned that determinant and pronouns are likely, but it put them in 2 different bins, 2 different latent states. So this is a latent dynamic conditional random field. And another one that's and that's one of the last one in the family of conditional random field before we get into the multimodal. But it's the idea of having only one label. What if I have only one label? I have all these words and I want to know the sentiment over the whole sentence. Then the hidden conditional random field allow you to do it. What it will have potential between the hidden state. It will have potential between the observed and the hidden states. That's the same. And then you have also the potential, and these will be shared between labels as well. And so the inference is tractable in linear sequence. And so you can train that using gradient descent. If you want to train the usual way, you will use more of a Newton-based approach. And instead of using stochastic gradient descent with batches, you may use all of the data. But this is non-multimodal. But what if you have multimodal data? And let's say that my input is both language and visual. There you can learn, you have a model and you can make it multi-view. What it means is your audio is going to have its own hidden dynamic, and then visual will have its own hidden dynamic. And then you need to pair it, the 2 of them. And one way to do it is to directly, or you could also do a coupling. But nicely, this model, what's really nice is that it allows the problem with doing the same as if you remember with the HMM is we had to couple temporally coupling things. here we don't need. The model allows us, because it's modeling those potential functions, allows us to directly model the co-occurrence, like potential of events happening at the same time, synchronously. And that's what's called a multi-view HCIF model, where your probability of y, that's what you want to model, probability of y, given your xa and xv and your trained parameter theta. And then the idea is to solve this simply by integrating over all the hidden state. And now this can be done. There's nice ways to approximate this using loopy belief. If you realize the problem here is that you suddenly have loops, and so you have either junction tree or loopy belief to do that. One of the advantages of the CRF is that I can not only model with conditional random field, but I can also bring neural representations with it. And so I can go ahead and take my representation, my input representation, and use neural network, and then on top of a CRF. And if you ask me, if you have CRF and neural networks and you want to merge them together, it makes a lot more sense to have neural networks at the bottom with where you have a high dimensional. And so we've seen beautiful work on like learning good representation, and maybe you pre-train that representation with another data set. And then the conditional random field allows me to put knowledge that I have over the structure of my label. And here, the knowledge I have is that it's a sequence, it's a temporal information. And so I will put that knowledge of temporal contingency in my model. And so the conditional neural field, what it will do, it will model my, my temporal consistency, and it will also model here my grouping. So what does this do? If you remember, it's a lot about clustering. It takes some high dimensional, embed it into some lower dimensional, and then take this and kind of cluster it into these different labels. That's what it's going to do in this. And so this is the this function here will be defined based on the neural network. And here, this could be as complex as you want. I mean, I put it only one layer, but it could be as many layers as you want. So this could be as many neural networks layers as you want. There's nothing stopping you from that. And now, as you can expect, people decided, hey, why are my representations not recurrent? And yes, you can do it. There's nothing stopping you from just going and saying, hey, I'm going to learn a representation for X that is contingent. So that's what the LSTM, but the LSTM is always, you always should think it more on the representation learning side. But I may have some knowledge that in that task, there is two things that's useful with the CRF. One is that my state has a nice discrete clustering that I want to take advantage of. And the second is that there is a structure, and here is a simple temporal structure, could be a little bit more complex, but and the nice thing is you can go and back propagate. The learning is feed forward, and then the gradient back propagation. So here you will do belief propagation for that part, and then back propagation at the same. So feed forward, belief propagation, and then back propagation. So what will be the number of parameters in this? So theta E will be based on the number of labels. So if you have 100 entities, so it would be 100 times 100. And as I just mentioned, what do you get from the LSTM? A lot of it is, in fact, from what you get from the LSTM is a little bit of a recurrence of your representation, but it's still in the representation learning phase. Here, what I get is I can integrate knowledge over my labels. And finally, you could go all the way, put everything in, and just say, hey, not only I want deep neural representation, LSTM, and also CRF. So there was this paper that brought everything together. And one example would be character embedding for that. I talked and gave an example at some point where I would like maybe to not just have my direct link with my direct neighbors. Maybe I want to do also continuous prediction. And so maybe my prediction here are not just discrete, but I want to predict something over time that is also continuous. And so in this case, the equation is really similar as a typical conditional random field. The problem is here is that I need to, like a conditional random field, I need to divide by the potential function and the partition function, sorry. And this partition function, in the case of a CRF, we had some little tricks to make it work because they were discrete states. But if it's continuous, you get that very infinite integral that you need to integrate over. That gets a little bit harder. And so for that, when you see this kind of like infinite, one thing you should think about this kind is to think about it right away as a multivariate Gaussian integral. That's usually a good trick. If I can take this equation and put it as a multivariate Gaussian integral, if I can make it in that form, then I have a closed form solution. What it means is that now I can't use any potential function or any feature function. They need to be feature function that will allow me to eventually have a formulation that is close to the multivariate Gaussian integral. And so this is one example that was suggested when this continuous CRF was presented. And so you can take this and because it's closed form, what's really nice is that it takes this the CRF conditional probability that you're modeling, and then now suddenly you don't need to go gradient descent and all this. There's a closed form solution, so it's beautiful. And then that one is related to the matrix of here, and then one is related to this. And so since CNF can be viewed as a multivariate, then the optimal of a Gaussian, like since it can be seen as a multivariate Gaussian, then what's the optimal of a Gaussian distribution? The prediction is simply the mean of it, and you can optimize. So yeah, and then what's really nice is like, as long as I can keep it into the multivariate Gaussian distribution, then earlier I mentioned that closed form solution is closed form solution for the inference of the probability. I will still need to do at optimization time do a gradient descent. Sorry for this typo. But the closed form solution is for the inference, so I can really quickly get the optimal Y. The high order allows you, if we use certain potential function, to connect anything with anything. And finally, you get to the fully connected CRF. And that's, as you remember, that was one of the examples I gave you. I said fully connected CRF is very interesting because now every pixel will be connected with every pixel, or at least I'm going to be connected with all of my neighboring pixels. And The challenge there is that to do the inference, it can get a little bit hard. And so what I will do is, in fact, look at it as a mixture of kernel. And if I do the optimization for this, I often end up doing this with an approximation using the mean field approximation. And we'll discuss a little bit the mean field approximation when we discuss next lecture, when we discuss a variational autoencoder. But yeah, mean field approximation. So it's not exact, but by doing this approximation, then I can get my, in one shot, I can get all of my prediction. And I can use, and that's one of the paper that is presented for today, and that's going to be my last slide today, is that I can use this idea of fully connected CRF to predict the action of every frame in the sequence at the same time, and not only allow for first order Markov assumption, but allow for every frame to be connected with all the other frames. And that's another example of bringing CRF with neural representation. If you look at the slides that are posted online, you can see a few examples of another example where the labeling of the CRF is not a hard labeling, but a soft labeling. And that's what's called a soft label chain. I invite you to look at the paper for more details. Okay, thank you very much for your attention.